So a very good afternoon to one and all present here. I welcome you all on day 2, session 3 of AICTE ISTE 1 week online refresher program on artificial intelligence and cooperative Noma 5G network. I would like to welcome our eminent speaker, Dr. Neelakandan Rajamohan from IIT Goa. It's my pleasure to introduce our speaker. Dr. Neelakandan Rajamohan obtained his PhD from IIT Madras in the area of wireless communication. At present, he is serving as an assistant professor in the School of Electrical Sciences in IIT Goa. Previously, he had been serving from the IIT DM, Kanchipuram and VIT University, Vellore. His research areas include signal processing for 4G, 5G wireless networks, massive MIMO, millimeter wave communication, and beamforming. He has published several of his research works in reputed journals, including IEEE Transaction and IEEE Communication Letters. I welcome you, sir. Now, I would like to invite Dr. Neelakandan Rajamohan to deliver his talk on hybrid beamforming for NOMA for millimeter wave communication in 5G. Welcome you, sir.
Yeah, thank you for the nice introduction. Yeah, okay, so I can share my screen. Oh, okay, so the slides moving and everything is fine, right?
Yes, sir, it's visible.
Fine. So, okay. So in this talk, good afternoon to all. So hope we have been getting through a very good series of lecture. Just I have seen the brochure. So you have very eminent speakers and very expertise are giving the talk in that. So just I am very happy that I am one among them. I feel proud and honored. Just I'm invited for this with such a good set of eminent speakers. Okay, so in this talk, let me just introduce about the several spatial modulation techniques and beamforming and NOMA, which stands for non-orthogonal multiplexes. So just without going into the mathematical details and intense treatment of or analysis of these things, let me just give you some overview about that and how that fits into the 5G communications and what is the roadmap ahead for our research. Okay, so I assume that our audience has some minimal background about this communications and digital communications. Though I have kept the discussion quite generic to cater the wide range of audience, but still that may have some information which might require some background. But still, if any of you are not comfortable, feel free to discuss with me to get more into that. Fine. So now. So the underlying reason why we are looking for 5G and 6G and beyond. So these things are generally the labels. But so 4G, it's under label or standard. So several technologies or techniques comes under that. So right now, the primary objective of that in 5G is can be thought of in different requirement setup. One among them is the capacity improvement. So under which all these technologies come into that. Not only that, there are several other requirements in 5G, like end-to-end user data rate, device-to-device communication, massive mission type of communications, and so on. So out of all the things, there is one pillar which requires or which necessitates from the 5G aspect is that this capacity improvement. So the current capacity can be interpreted as the way it has been illustrated in the picture. And what is the required capacity in 5G? Just it is a pictorial representation about what are the different ways of improving the capacity. Suppose as the fundamental Shannon's theorem says, capacity equal to bandwidth times 1 plus SNR. In the simplest possible way, it depends on the signal to noise ratio and the bandwidth, how much you are giving to me and how much interference free it is in the receiver end. Okay, so given this, what are the different ways of improving your capacity? So one aspect, say as the blue line shows, give me more transmission bandwidth, so I can increase your capacity. So of course I can think of many users can be supported, or I can give them more data rate if you give me enormous amount of bandwidth. Okay, so if you want enormous amount of bandwidth, what you have to do? So you have to communicate in the ultra wideband. So there are a lot of white spaces available in the UHF band. You can go and communicate there, or else go for millimeter wave band. So where there is a vast spectrum is available, which is underutilized a lot. So you can go and communicate in this band. And another is cognitive radio. This cognitive radio, somehow, though there are many research works on the paper, but it has not been demonstrated in the market, or there is no proven ability of its cognitive radio in the practical aspect. And another side, if you think another direction in the red color arrow, what about the spectral efficiency? The spectral efficiency, that stands for, if I have given you fixed the bandwidth, say given B, how much effectively you can communicate in terms of bits per second. So as we know from the first principles of Nyquist, Nyquist first criterion, second criterion, and all, we have several criterions which tells you about given the bandwidth, what is the bits per second you can communicate. So this is something relating between analog bandwidth and the digital rate. So one thing I want to emphasize, though many of you might be knowing that, just to keep you on track and without overlooking anything, irrespective of whether that is digital communication or analog communication, the signal being transmitted just out of the antenna is continuous in time. That's an analog signal. The information embedded in that is in the digital form, but the signal is always continuous and analog, whatever being transmitted out of the antenna. Okay, so that is one thing. And we generally say the bandwidth in terms of the heads. Suppose if you ask me what is the bandwidth of one particular channel, or what is the bandwidth of a cable that can support, we generally say that it is 10 kbps, 10 megahertz cable, or 10 megahertz bandwidth. But when we talk about, suppose I give you from 1 megahertz to 2 megahertz channel, so that is in the bandwidth is in the form of analog, what we generally conceive or interpret. So given that bandwidth, what is a bits per second, how many bits you can communicate? So that's what the limit it says, what is the best you can do. So if you think in that aspect, spectral efficiency deals with that. If I give you 1 hertz, how many bits per second you can communicate with? Okay, so out of that, how we can improve the spectral efficiency is that going for massive MIMO techniques. MIMO technique stands for that multi-input, multi-output systems. The term massive connects to that. You have thousands or hundreds of antennas at the base station and the receiver. And what is the best you can achieve if I give you such a kind of a system? However, how we can get massive MIMO? Already we have some number of antennas in the current standard. So can you simply go and scale it to a higher number? So that we will answer shortly now. Another side, as the green color arrow mark shows, the frequency reuse. The frequency reuse is about, again, given the bandwidth, what is the number of times you can use the same frequency band across different places. So people generally might have shown with the cells, if you have seen, if reuse factor 1, which means that you are just in the nearest adjacent cell, you are using the same frequency band. So when you are making a call with a particular channel, in the next tower is giving the same channel, the same frequency band to someone else in the adjacent channel. So that is what frequency reuse. So out of that, what will be the problems like interference cancellation, and you need some cooperation among the towers, which frequency band you are giving to whom and how it communicates, how far that user is from you. If he is from the farther edge of the adjacent cell, you are in this leftmost edge of the another cell, then you can avoid the interference. So that needs some kind of a cooperation among the towers. And IoT and massive devices, and how to predict the traffic load. So these are all the things that confronts us when we think about the frequency reducing methodology of capacity improvement. Okay, now in this talk, first let us just pitch on the millimeter wave communications out of the 3 different directions, and we will connect that band when we are given enormous band, what we can do that automatically have some kind of inherent underlying connection with the another red color arrow where you can employ massive MIMO technique. When you employ both massive MIMO in the millimeter wave band, what are the different sophisticated signal processing you can employ? That's the other side of the green arrow will come together in the knot. So that is how the rest of the talk is going to be. So initially I will go in a very slow pace so that though I am not able to cover the entire slides within the stipulated time, so that if I give the fundamentals very clear with the help of the slides, you will be able to understand the rest of the things just by going through the slides and the references therein. So even the pace of my lecture talk is not up to the number of slides within the time, nothing to bother about that. So I will make the fundamental part of it very clear so that the rest of the slides can help you to go through that. Oh. Out of this, so now let us come to the millimeter wave band, as I already said. So generally the millimeter wave frequency is like it is not, there is no clear cut definition of, oh, this is what a millimeter wave frequency. People generally, when you compute the light velocity, divide the light velocity divided by frequency, wherever the wavelength comes in the order of millimeter, they call it as millimeter wave. But generally, whatever we have in the current communications, whichever is happening so-called in the microwave band, there we have up that can be, I mean, whatever the technology you invent new, that can be simply add on or built on top of the existing infrastructure without any additional problem. That highest frequency is up to 6 GHz. Once you cross 6, then whatever the techniques, channel models, analysis, mathematical treatment, everything becomes invalid once you cross that. So we may have to redo everything from the beginning, starting from the channel model, all the way the network planning, everything must be totally different when once you cross 6 GHz. So whatever we have already done, the clear basement, what we have made is valid up to 6 GHz. So that's why people generally say that sub 6 GHz and above 6. Even when you talk with the vendors, they follow the same notion. And above 6, the feasible band was found between 24 and 100 GHz. And again, there is a lot of space available beyond 100 to 300. But there has been some experimental evidence, particularly if you look at the literature by Rappaport and others. So it has been found that there are certain feasible bands where you can communicate in the millimeter wave frequency, meaning that which band allows you to communicate. That's what it is. What are the challenges and what we have to do in addition to that? That's the rest of the story. But will you be able to make your own communication system in the band or not? That's what the question. Yes. So what are all the bands? So that is what the several color strips showing you that where the bands available. Now people have thought that the typical band where we are communicating from 3 to 4 GHz is almost saturated. So we have no space left. So now we have slowly going to migrate into the higher frequency band and then see what are the feasible things we can do. So one part, what will happen when you increase the frequency? The very first thing one has to think about, when you go higher and higher in the frequency, the range comes down. Range means the signal, how much the signal can travel without getting attenuated below the noise floor. So for the given transmission power level, given the same environment, once you increase the frequency of operation, the range will come down. That's why in the earlier radios, if you remember correctly, even you can listen to far away AM stations, amplitude modulated stations, but not the FM stations. You might have one FM station just for your own city, not beyond that. So that is how typically things work. When we had the earlier small radio sets available, still that can be found in some of our places. So because AM station frequency range is in the order of kilohertz, whereas the FM stations operate at the megahertz range. So automatically the range comes down by a larger factor. But now the way the FM operates is different. You might, if you come to know, just if you check in your app, that Radio Garden, so which was given by ISRO, so that you can choose any FM station across the globe. If you just install the Radio Garden app and open it, and you can see all the FM stations in the globe as tiny dots on the globe. You can go and choose a particular station and play it out. So, but that's a different, yeah. Anyone is trying to ask something? Okay. Okay, fine. So that is in the backbone satellite network band. But otherwise, if you think of AM and FM, the range comes down by a larger factor when you think of the FM signal. So like that, when you go for higher in the frequency than what we are operating now, the cells what we have the coverage by the given tower for the same transmission bandwidth comes down by a larger factor. Is there any disruption from my side?
Participants, kindly mute yourself during the session.
Okay. Oh no, fine. So now when you think of the same transmission power, since the range comes down, we may have to install many number of towers to cover the same coverage area. So that's how it will happen for the one cover cell. We may have to have multiple cells to cover the same coverage area. So obviously, if we come to know that some things about handover, so network planning, everything will happen. But still, we will come to those challenges shortly. Excuse me. So now, another advantage. So what will happen when we employ this massive MIMO structure in the tower when we operate at the millimeter wave band? Before that, just I have to tell you something what it will happen. So suppose when you go for higher in the frequency, as I already said, one thing, range will come down. Second, the signal will become highly directional in the sense that the signal will not diverge. So it will travel in the same line of sight. So what will happen once it starts in the same line of sight, the interference comes very low because the signal doesn't diverge. So automatically you are getting the directional gain. Another side, when you go higher in the frequency, wavelength comes down. One important aspect we have to think about, suppose if you have to install say 2 antennas. So you have some RF section, RF front end panel in your mobile phone or any receiver, wireless receiver. Say you have one antenna. Suppose you want to have more multiplexing gain in the sense that, as we know, our wireless channel has the nature of multipath. So since there is no dedicated wired channel between the source and the receiver, once you start transmitting the signal, it will just go multiple path. It will go all along the way and come back to you. So it will have multiple reflection path and multiple scatterers around the way. So, but what will happen when you have one antenna? So you have one particular, after the multiple path, you have one certain virtual channel between you and the transmitter. Suppose you additionally mount one more antenna. So now you are getting another channel between you. Now what will happen when you place the second antenna? You have to place it at least λ/2 separated. Then you will get some additional so-called multiplexing gain because of your one more additional antenna. If you place the second antenna again very close to the first antenna, then these two antennas will behave as if there is only one antenna. So in the sense that if you would like to have the benefit of multiplexing gain, then you have to place it at least lambda by 2 separated. Okay, so this is one information we have to keep that in mind. Currently, we are operating in the 4G and we are operating in the LTE technology, where we have two antennas at the receiver. Now, I don't want to increase the size of the phone. If I have to again additionally mount, say, two more antennas, I have to separate them again lambda by 2 from each other. So automatically my front end panel size or a front end size will grow, right? So, but generally people won't prefer very enlarging the enhancing the size of the mobile phone beyond certain extent. But what will happen when you go for higher in the frequency? So between the microwave band, microwave signal, what we are operating now, from that wavelength to millimeter wavelength, we are going down by a factor of 10 power minus 3, almost. So the wavelength of millimeter waves is 1000 times lesser than the wavelength of microwaves. So what happened? The same space what you have already installed the two antennas, since the wavelength comes by a factor of 1000, still by maintaining the rule of lambda by 2, you will be able to place 2000 antennas in the same space. At max, the provision gives you. Just a number for convenience we have taken. So which means that without enhancing the sizes of any of the transmitter or receiver antenna panel, you can mount thousands of antennas in the transmitter and the receiver. So now we have inherent connection between the massive MIMO and the millimeter wave. Now, what is advantage once you have thousands of antennas? Yes, there comes into picture like one aspect is beamforming, where you can create the signal and adjust the phases of adjacent antennas such a way that they coherently add towards a particular direction. That's what the technique referred to as beamforming. This is one simplest example technique. But once I give you thousands of antennas working independently or in an uncorrelated way, more preciously and technically speaking, then the signal processing at the front end can be made very effective, given that you have thousands of antennas or multiple hundreds of antennas in that. So that's what I have summarized here. And there may be some disadvantages like pilot contamination, correlated fading, like that. So those things are quite in depth into the wireless part. So let us just see the other things. Like, so whatever we have discussed has been given in the picture. Typically in the conventional MIMO, we have around 2 to 8 transmitting antennas at the tower, and the receiver has 1 to 4 ideally. And in the case of massive MIMO, transmitting antennas may go up to 100 or 1000 even, and the receiving antennas can be thought of up to 16 to 64, because mobile we cannot have much. And further, and over and above that, when you have multiple antennas, not only them, you have to have another hardware series of elements, so-called RF chains. We will come to that part in the subsequent slides. So packing many of them in the adjacent very smaller area may create some issues known as electromagnetic compatibility, EMC, and electromagnetic interference. So those things come into picture, which is something the physics part of the EM wave propagation. So ideally this is what envisioned, but now we have the software defined radio SDR platforms, which have come up to 64 cross 64 and all the way up to 128 cross 180 for certain band of frequencies. So beyond that, we don't have any experimental setup to verify what will happen if you have 1000 antennas or whatever. So people are still working on developing some test beds and test benches for these things. So this is what when you create a normal base station, how technically we are trying to do something known as sectorization. So around the tower, there will be 3 different antennas. Each one is working for 120-degree sector around it. So that will cover some circular section of it with 120-degree subtending angle at the center. So like that, there will be 3 towers covering overall 360-degree directions. But now the total technology will be different. we will try to create beams towards the different users, so-called beam forming. So I won't cover all the users with a single coverage area. The coverage area becomes virtual. For every user, I can create beams to transmit the information towards them. So this is one quick example or quick explanation about what is happening in the beam forming. So when you have, say for example, you have antennas mounted on the plane, like in the so-called uniform linear array, in the sense that all the antennas are separated at a distance d, and say one wave is coming and just hitting like this in a particular angle. Right. Now say when you look at it, when you draw the normal, the first part of, when you think of the far field, so where it's like a uniform plane wave assumption, once the part where it is reaching at the rightmost antenna where my cursor is, then the next immediate antenna, the signal here has to traverse slightly more distance to reach here, and so for all these antennas. Right. So after this has arrived at this antenna part, gradually the amount of distance all these antennas experiences from the signal is increases. So when you have different delay, that is reflecting the Fourier transform as phase shift. So when you compare, say for example, if you draw one sine wave, so all of the sine waves are here. Just imagine like one bunch of sine waves standing on this plane wave, for instance. Then everything is hitting at the zero phase, for example. Then after that it will hit after say 30-degree phase. This may be at 45 degrees, 60, 75, like that. The phase, it will incur more additional phase shift when they hit at the antenna. So now if you adjust your phase shifters connected to this antenna such a way that you undo the effect. Suppose this is experiencing additional 30-degree compared to this, then you pull it away back by 30-degree. You just multiply by e power minus j5. So you rotate the phasor in the opposite direction again to bring it back. Though in terms of the complex baseband, we say that rotating in the opposite direction. But in practice, what we are trying to do, we simply again advance those waveforms or just realign them in such a way that they coherently add at the receiver. So if you add like that, then automatically for a particular angle theta, the signal will, all the signals will sum up and they get maximized. In other words, if you have to pick up a signal, if you have to pick up a signal at a direction theta, so if you have to make your phase shifters like e power minus j5 particular angle where the angle is given here. If you assign your phase shifters in such a way that, then automatically that will pick up the signal from the direction, and the same principle applicable for transmitter side as well. Okay, so now with the given massive MIMO, now we have two back-to-back requirements. One is the spectral efficiency, as we have already discussed. Another one is energy efficiency. So the spectral efficiency, we have already defined what is it about, given the bandwidth, how to increase the bits per second data rate for your end-to-end user communication. And the energy efficiency, which means that when you spend 1 joule of energy, what is the amount of data rate in bits per second you can get. Now we have already discussed about this point. When you have certain amount, a certain data stream, for example, one complex information stream comes into the baseband precoding, that will flow through the digital to analog converter DAC, and then some low noise amplifier followed by filter, everything. So which are referred to as the RF chain, which contains the entire series of hardware elements, and then go to the antenna. But when we discuss about the massive MIMO, where we have to have several thousands of antennas or whatever, then having those many RF chains is in the antenna's transmitter side is practically infeasible in the sense that the amount of power it will consume is enormous. In any transmitting element, the most power hungry devices are the RF chains. Once you have more number of RF chains, then the amount of power it consumes becomes very drastically increasing. So then what people think about, you don't give all the RF chain, every antenna is not connected to every RF chain. We will have some kind of a suboptimal architecture, which we will discuss in the subsequent slides. Before that, there is one other way of improving the energy efficiency. One thing is that now we have to keep that in mind here. Say I have 1000 number of antennas here, but I cannot have 1000 number of RF chains in the antenna panel. So one aspect I can come out of the problem. Don't give RF chains to all the antennas. Give your RF chain only to a subset of it. Okay, so at a time I will not give connection to all the antennas. Say I will have only 100 RF chains. So 100 RF chains will be can be connected to say 100 antennas. Remaining 900 I won't connect. So this 100 may differ from one transmission to another transmission. Let us see that. But one aspect is that I won't give RF chain to all the antennas. Second, let me make the RF chains share the antennas in the sense that one RF chain can connect to 100 antennas, and so the 10 RF chains or whatever, they can connect to 1000 antennas. Now these two kind of different approaches I can think about to reduce RF chains. Now let us think about the former in the sense that if I don't connect all the antennas with individual RF chains, I just connect only few of them. For this approach, can I do anything on top of it so that I can get some additional benefit? So what can be done? To see what can be done, we have to see something which is known as spatial modulation. Just let me briefly tell you what is it about, since we have come across amplitude modulation, frequency modulation, and so on. But the term spatial modulation is something new, which started to coined after once we think about massive MIMO architecture. In the spatial modulation, what happens? Say suppose you have 4 transmitting antennas as shown in the green dots here. Now, how many RF chains I need? I need 4 RF chains, right? Now, if you have 4 RF chains, you can simultaneously transmit. In the 4 antenna, you can transmit independent data streams. If you have one RF chain, you can have one independent data stream. So every RF chain can have its own data stream. Suppose if you are employing, say, QPSK signal constellation, if you know from digital communication background, the QPSK transmission can have 2 bits per every transmission. So every antenna can have 4 different bit streams. So totally you can communicate 8 bits per channel use, right? So once you transmit, that signal can carry out 8 bits, right? This is one approach where you have to give RF chains to all the antennas. Now, I don't give all the antennas with I don't equip all the antennas with RF chains. Say I have only one RF chain. So this one RF chain can connect to only one antenna, right? So I have, by means of a switch, I will just connect any one of these antennas. That's what I can do because I have only one RF chain, right? Now in one RF chain, that brings.
టాక్స్ అన్ని బానే ఉన్నాయి కానీ మన కుదరట్లా. ఫిజికల్ గా అయితే ఫిజికల్ వెళ్ళాలి అలాంటివి.
Okay, so now in the every transmission that brings 2 bits of information. Then we take additional 2 bits of information which will determine which antenna this RF chain is going to get connect. So now suppose that I take 4 bits at a time, say 00 followed by 11. Now the first two bits which are meant in magenta, so that 00 tells me that I have to transmit this complex symbol. So that is 1 plus j. And next, second two bits tell me which antenna I have to activate. So if I assign 2 bits to every antenna in such a way that 0001, 1011, then the second by a couple of bits dictate me that I have to activate the fourth antenna. So then what happens? The RF chain brings the data symbol 001 plus j to the RF front end and connects that with the switch to the fourth antenna. Now out of the 4 antennas, the fourth antenna will transmit. All the remaining 3 antennas remain silent. So now what happens? Without transmitting anything from the 3 antennas, we are communicating some additional bit of information. So that is what we refer to as spatial modulation. So in the sense that we modulate the space, the spatial information, the index of the antenna, spatial index of the antenna carries some additional information. So that's what the term refers to as spatial modulation. Now the transmitted vector will look like 3 zeros followed by 1 plus j. So this is what the transmitted vector now. Now if you think of how many bits we are communicating now, 2 bits carried by the complex symbol and another 2 bits where which antenna is being activated. Now we have communicated only 4 bits per channel use. So when you compare with the full architecture where it is taking 8 bits per second, so the 4 bits is only half of it. 50% gain only you are getting. However, what is the reduction in the number of RF chains? The full multiplexing architecture requires 4 RF chains, but now you have only 1 RF chain. So at most 75% reduction in your energy consumption. So that's why this technique is popular among the scientific community of these transmission technologies, in the sense that it is bringing you some energy efficient communication. Okay. So additionally, one thing we have to notice here, if you think of say 1024 antennas at the base station in the case of massive MIMO, then just by activating any one antenna out of them, you can communicate 10 bits of information. And also you can make your transmission more sophisticated. Instead of one antenna, you can activate a subset of antenna. So then you have NCR combinations out of 1000. If you choose 10, so now you have 1000 choose 10 different combinations are there. So every combination can convey certain amount of information. And if the receiver is equipped with to such a way that it can identify which antenna is transmitted, then it can decode all the transmitted spatial information at the receiver without any additional energy consumption. Right. Now there are several variants of spatial modulation where you can activate one antenna out of them, or something known as generalized spatial modulation, where you activate some subset of antennas out of the available transmitting antennas, or in the case of QSM, the quadrature spatial modulation, where you activate one antenna to carry the real part of the complex symbol and another antenna independently to carry the imaginary part of the complex symbol. So like that, there are several other variants of these spatial modulations. Each one has its own merits and demerits. Now we have to think about this another low complexity technique which allows you to do your computation in an efficient way. So before going further, just I will introduce you some the concept of compressive sensing, which generally deals with recovering from the underdetermined system of linear equations. So first I have to tell you what all these things. Then automatically the CS framework, what we refer to as compressive sensing framework, how that is fitting into the problem, what we are looking at now. Then that is how this kind of AI and ML techniques started to evolve in wireless communications recently. So let me just give a brief introduction about that. Then I will connect this part with the discussion going on currently. So in generally the compression or compressive sensing, these terms were quite common in what we call it as image processing. So where we have some original image, you compress it and store it or transmit that, and the receiver or when you get it, you recover it back. So there may be some lossy compression or lossless compression based on how much data you lose or how much clarity you miss, like based on this. On the other hand, compressive sensing deals with recovery of sparse signals. What do we mean by sparse signal is that a signal is said to be sparse if the number of non-zero entries in the signal or the signal vector is far lesser than the dimension of the vector. So like the one what is shown in the figure, which has only 2 non-zero entries out of many, I think it's 9-dimensional vector, but it has only 2 non-zero entries. So such a vector is known as sparse, and just opposite of dense. When you have sparse signal, so what can happen? So that is what something known as sub-Nyquist sampling technique. So just let us see the signal f of t, which has 2 frequency components. One is at 53, another one is at 531. Yeah. Now, as per the Nyquist theorem, what it says, if you have to store the data, you have to digitize the data. First, you have to sample that. So the sampling frequency must be at least twice the rate of maximum frequency present in the signal. Okay, so now the maximum frequency is 531. So you have to sample the data at 1062 Hz. Okay, if you sample and compute the power spectral density, this is what we recover. Fine. Now, just let us note the signal carefully. The Nyquist theorem of low pass signal sampling, say if we have a signal which has the frequency from 0 to B. So the Nyquist theory says that you have to sample at the rate of 2B samples per second. But that assumes that the signal has frequency components from all the way from 0 to B. So in this case, it is 531. So the underlying assumption behind the Nyquist theorem is that when you, for the low pass signal sampling, if the signal can have all the components from all the way from 0 to 531. So that is what the underlying assumption on developing the low pass signal sampling technique. But in this case, we don't have almost all the frequency component. Just we have only one here and another one is at the end. Then the triggering thought is about, can we reduce the sampling rate taking this into account? In the sense that the signal does not have all the frequency components, can I sample at a lower rate than what Nyquist dictates? And can I get some reasonably good performance as compared to that original Nyquist sampling technique? So that is what the right side of the figure, where we sampled the sub-Nyquist rate, which is far lesser than the Nyquist rate dictated by this 1062. But still there is it recovers the frequency components correct. However, the difference between the components is not correct as it is. It has PSD has both the values equal. So almost the estimated value here is almost equal because of the digitization process. But here the difference is more, meaning that you are not perfectly recovering. That is fine as far as you are okay with that slight degradation in the performance depending on context of your application. So this is what the overall idea about a sub-Nyquist sampling technique. So in the now recently, this compressive sensing or sub-Nyquist sampling opens the completely new era or new platform for the physical layer signal processing in the wireless communication. Okay, now let me just briefly see in terms of mathematical notation to keep you on the track. Suppose we have a linear observation model, say y is equal to ax, and okay, at present you you ignore the noise. You have y is equal to ax. Y n cross 1 matrix and A n cross m and x m cross 1. Now the problem is to recover x given y. I will tell you what is y. You should tell me what is x. You have to recover x. You know A. Now if with the full rank n is equal to m, that becomes a square matrix. So obviously just we can invert. A inverse y will give you the answer. Yes, the solution is unique. And suppose that if n greater than m, where n is a tall A is a tall matrix, n is greater than m. Then, so when you have a over-determined system, tall matrix, the solution may or may not exist but the solution will be unique if it exists. So if it has a full column rank, and if n less than m, meaning that the matrix is fat, if you have more number of columns than rows, say it is a 3 cross 5, 10 cross 100 like that, which is an underdetermined system. So it doesn't have unique solution at all. There may be many solutions that will satisfy the set of equations. Typically, this is something like you have given me 3 equations with 5 unknowns. So the traditional wisdom of linear algebra that says that number of unknowns must be equal to the number of equations. If you have 3 unknowns, give me 3 equations, I will tell you what is that. But I have 5 unknowns, but I give you only 3 equations. So automatically there will be 2 free variables, so-called. So they can, multiple of them variables can satisfy the same set of equations. So that's why the uniqueness fails. But if there is no uniqueness, then you cannot communicate. When you transmit and receive, you must be able to uniquely determine what is that. So there is no ambiguity in the reception, right? So how to get that? Now, what CS framework tells that unique solution possible even if you have n far less than m, in the sense that you have very fat matrix, say you have 100 unknowns, but you have only 10 equations. So you have 10 cross 100 matrix. Still it is possible to recover when 2 conditions. The unknown vector x must be sparse, in the sense that even though you have a 100-dimensional vector x, not all of them have the non-zero entries, meaning that the matrix is not cannot have all the values non-zero. The number of non-zero entries can be anywhere, but say it cannot exceed certain number. For instance, there is one restriction on the number of non-zero entries, which makes the signal sparse. And that number of non-zero entries again must be far lesser than the dimension of x. Next, you cannot arbitrarily choose the matrix A. If you have to choose them systematically, that allows you to recover the 100 unknowns with 10 equations. The matrix A in the literature of CS we refer to as sensing matrix. Now the unique solution is guaranteed with sparse X and the proper choice of A. If these 2 platforms satisfy simultaneously, then there is a way to uniquely recover the signal. Sometimes, like the model what we have shown here, so you have on Y, number of observation is far less than the number of unknowns. Right. Sometimes the underlying signal may not be sparse in some applications, but you can make them sparse by think of some linear transformation, unique linear transformation, what we refer to as change of basis. Suppose if you have all ones, right, it is not a sparse vector, but if you take a DFT of it, it will become 1 followed by all zeros. So you have to find the right basis where the signal becomes sparse. So that is, but for all the signals, for all the models, we cannot say that such a formulation can be followed. If at all the underlying problem allows you to apply this framework, yes, you can. This is the way you can do. And there are different CS models. One is the standard CS model where we have one Y vector, a fat matrix, sensing matrix, and the unknown sparse vector, which has some far few number of non-zero entries here and there. And another model is something known as block sparse model, where the number of non-zero, the non-zero indices appear as blocks or clusters. And another side, we have multiple measurement vector CS model, where we have from the different sensing values, you can sense with the different unknown vectors, you sense and get your observation. And the generalized multiple measurement model, where you measure every unknown vector with the different sensing matrix. So all these models can be fit into different problems of in wireless communications based on the application and the context. And what are the necessary properties of the sensing matrix we think about is that one is a restricted isometry property. Essentially, if you think about the property in an intuitive way, suppose you have one 10 cross 100 matrix. Okay, now let me show this picture for convenience. say now you have this sensing matrix 10 cross 100. Now you want to find its ability to recover a sparse vector S, which may have at most 5 non-zero entries. So this is 10 cross 100, this is 100 cross 1. So we have 100 unknowns, but out of the 100 unknowns, only 5 unknowns will be non-zero, all other things will be 0, but you don't know which of them are 0. Every time the number of index may change, right? You cannot say that only first 5 entries are always non-zero. Then you can automatically grow the 6 to 100. Any 5 entries can be non-zero. So if you want to know the ability of the model to recover those 5 non-zero entries, the one way is to have that. If you take any 5 columns randomly out of the sensing matrix, its eigenvalues must be close to 1. More and more it is close to 1, better it can recover the sparse vector. That's what the restricted isometry property says. On the other hand, mutual coherence, which talks about if you take any 2 columns randomly, how much they are correlated. So these 2 properties determine how effectively you can communicate or effectively you can recover that. Now, coming back to our original problem of the spatial modulation I have already talked about. Let me just go and show something pictorially since I have few more minutes left with. Okay, now let us come back to this another one modulation technique which is known as receive spatial modulation. So here what we do, we activate the antennas and create a beam in such a way that you just point your signal towards only one antenna at the receiver side. So that is what referred to as receive spatial modulation. Right. So with these 2, transmit spatial modulation and receive spatial modulation and the background on CS framework. Now I introduce the NOMA concept too now. I think just let me skip that. If you have some understanding about the basic pre-coding technique, zero forcing equalizer. So this is nothing but the zero forcing equalizer. And what happens now, how many bits I can communicate? Just let me show you that the picture here. Say now I have some transmitter and receiver. I have many antennas, just I group them into different group like uniform linear array 1, array 2, array 3, array 4 like that. Just I have taken for 4 for example. And receiver also I have 4 groups. Now I will activate out. So the GT represents the number of groups at the transmitter. GA represents number of active groups at a particular time. In this case, GT is equal to 2. Sorry, GT is equal to 4. GA is equal to 2, meaning that I am going to activate any 2 groups out of the 4. And similarly, how many ways I can take GA groups out of GT? GT choose GA. However, since I am going to communicate the binary, I am take the log 2 and floor of it will tell me how many bits that can convey. And similarly, there are GR groups. Okay, and out of the GR groups, I am going to activate only GA groups. So that can convey GR choose GA floor of it. Those many number of bits it can convey. Next, now I have GA active groups here, GA active groups on the receiver side. Now which group communicate to which one? There are GA factorial ways of matching that. Next, in every matching you are communicating one complex symbol. So log to M of times GA times. Then you employ the receive spatial modulation as I have shown in the picture. Out of the many antennas in the group, you just trigger only one out of it. So which one? That can convey log to NR information bits, where NR is the number of antennas in one group. So now that is what referred to as hybrid transmit receive spatial modulation. So you have transmit side spatial modulation, you have receive side also spatial modulation, and you have multiple degrees of ways you can increase your bits per channel use as you can see in the rate. Okay, and as a, though I'm not going into the math details of that, this problem can be casted as a block sparse signal recovery problem in compressive sensing framework. Now Just I have shown you that for the numbers I have chosen, say incoming bit 1. So totally you have these many number of bits will be taken at a block. That let me show this figure first and then come to this. So now you have, this is your 11100100. These many bit a block has been taken at a time, and but by parsing that accordingly, every bit will determine what we are going to activate. So now, for example, transmit antenna side, what are all the possible groups? I can activate 3 and 4, or 2 and 4, or 2 and 3, or 1 and 4. Similarly, on the receiver side. And once you activate two groups here and here, there may be 2 different ways of matching them. So that can carry on additional information. And again, you take one complex symbol to activate one antenna out of it. So that's what the picture shows. Now I have activated 2 groups are the transmitted based on one pair of bits. Next pair of bits determine which antenna group I have to activate at the receiver side. Then how many ways you can match the GA to GA? There are GA factorial. GA is equal to 2. So 2 factorial ways of matching that. So you have to pick up 1 based on the another information bit. So that dictates me that 1 to communicate to 3, 4 to communicate to 2. So that is what the final decision. Then out of every group, this group takes one complex symbol in the magenta, and this group takes another complex symbol in the purple. So you have 2 times log 2m. That's what this 4th component. And in the blue and this magenta array, we have NR number of antennas. We are going to activate any one out of it. So that will convey log 2 NR GA times. So that is what it says. So finally, when you have this kind of structured way of communicating and you apply CS framework with low complexity, your receiver can do a better way with lower complexity. However, like the another case of activating all the antennas may have higher data rate. However, what will happen? It's energy efficiency in the sense that the number of RF chains is very large compared to the scheme. So by significantly reducing the RF chain, we can do better. So that's what the same scheme, just another pre-coding scheme. I skipped that since you can see from that part. I have to tell you one more thing about the NOMA before I leave the rest of the things to you. Once I make this clear, and the rest of the things are quite straightforward. So let me spend some time, few minutes on this NOMA part, then I will open to questions. Now, what is NOMA? Non-orthogonal multiplexes. So what is orthogonal multiplexes? Whenever you say orthogonal resources, right? Whenever you say the orthogonal resources, that means that the resource can be time or frequency or code, whatever. But when you say orthogonal, they are operating in 2 different bands. Say in terms of frequency, for example. Now you have 2 different frequency band as in the x-axis. So one user is communicating in the blue band, another one is operating in the red band. So what the receiver can do, they can tune to only your own frequency and leave it. You don't have any problem about that, right? But what will happen since you have taken whole band into 2 different user chunks and they are orthogonal to each other? Yes. But what is the benefit of doing this? Anything advantage? So what? For the same transmission power level, say you are transmitting at some certain power level, P1 and P2 for user 1 and 2. And of course, there one user might be far away, one user might be closer to you. Somehow you have to adjust the power level so that the total power is constant. And you have to maximize the sum rate. What is the rate you can communicate to 2 and what is the rate you can communicate to 1. Okay, so what is achievable rate for R1 and R2? Okay, so that is what one graph, one aspect, what you can do. That's what OME or orthogonal multiplexes. Now, the non-orthogonal multiplexes, look at the figure carefully. Instead of dividing the whole band for one user and 2, both the users are now operating at the same band. So in your capacity formula, B is total band. Now in this case, previous case, B was divided into 2. Now B is equal to same for both. So both of the rate can increase. Plus what we are going to do now. Then look at it, the figure. Let us assume that user 1 is very closer to the tower and say user 2 is very far away from the tower. So automatically user 1 channel will be very strong, user 2 channel will be very weak. Now you have to do some superposition coding on the data transmitted. What is that? Since user 1 is very close to you, then add the power or give the power to that user 1 data very low and add user 2 which is far away, give more power to user 2 data. Now what will happen at the receiver for both UE1 and 2? Let us think about simple calculation about it. H1 is very high, P2 is very high. So the effective gain P2 times H1 will be very high. For what? User 2 data, right? Now the user 2 data will be very high at a very good SNR at the user 1. So now you estimate the data and cancel it out from the observation. Now you will be left only with your own data. So that is what successive interference cancellation. The term successive comes from the fact that if you have many such users, 1, 2, 3, 4, 5 with different power levels or different distances from the tower, you make your superposition coding in such a way that each one decodes other weak users data and gets its own intended data from the tower. So that is what the SIC. What happens at user 2? Now user the H2, the channel gain is already weak. You encode P1 is very low. The effective gain of the user 1 data P1 times H2 both are low. So it will be very, very low at the user. On the other hand, P2 is very high. P2 is very high, but H2 is very low. Somehow the product H2 times P2 is moderate so that you can communicate. So that's why the P2 is already suppressed. So UE2 will do nothing. Simply take the user 1 data as interference and decode. So this is what the fundamental principle of NOMA, where you can communicate with all of your information by properly dividing the power into them. Okay, so with this, I stop and open for some questions, and the picture shows that where you can combine both the spatial modulation, hybrid beamforming, and NOMA in the single architecture, and the details are available in the citation given in our research work. So rest of the things are quite straightforward, and with the background you will be able to follow that with the slides. So I open to few questions now before I wind up for the session. Yeah.
Dear participants, if you have any query, you can unmute yourself. Any query from participant side?
Hello, sir.
Yes, please. Hi.
Hello. Hello, sir. My question is related to that arrays for the massive MIMO. Arrays of the antennas are preferred for the better efficiency and all that. Just know what you said. But if we use an arrays of an antenna, no doubt the antenna gain increases, but bandwidth reduces. So, is it possible to transmit more of the signals with that less bandwidth? I'm confused to this related to that arrays of antenna and bandwidth. So, which antenna we prefer? Can we prefer a single antennas or arrays only?
Okay, just before that, may I understand why do you connect the bandwidth with the antennas? What you are trying to say by that?
Actually, arrays are used no, so for better efficiency and all that. If suppose for one is two multi-transmitted signals, then
Yeah.
we use an array of an antenna, arrays antennas.
Yeah.
So related to that, if we use the arrays, then what change it causes in the transmission of the signals, whether it increases the bandwidth or reduces the gain. This I want to know.
Okay, okay. Let me answer to that. Okay. So suppose if you one point, let us observe that the bandwidth has directly nothing to do with the antennas. So antennas will just transmit whatever you intend that to do. So that is just a one like a transmitting element. Now, suppose if you have many antennas, what you can do is, suppose if you have only single antenna and you can communicate only a single receiver. With multiple antennas, you can multiplex the multiple users' data and you can transmit to all of them and do some pre-coding technique at your transmitter so that every user gets minimal interference from the other user's data. So these kind of some additional signal processing can be done if you have many antennas at the transmitter side. But if you want to have many antennas at the transmitter side, the frequency of operation what you are going to transmit should allow you to do that. So that is how the massive MIMO requires the frequency of operation to be in the higher frequency side like a millimeter wave band. And the resource allocation and how do we pre-code the data and avoid the inter-user interferences up to the baseband processing side before we transmit to these antennas. Yeah.
Okay, sir. Thank you.
Sir, this is Mangal Singh from Symbiosis Institute of Technology, Pune. Am I audible now?
Yes, yes, please. Yeah.
Sir, just apart from this, just I would like to ask something about the spectrum sensing in cognitive radio with some compressive sensing or all. Can you highlight some of the things, how we can start the research in that direction and what are the things that is available?
Okay, so the recently, again, as I said, the sub-Nyquist sampling, because in the cognitive radio, you have to sense a wide range of spectrum for the users. So there were several approaches proposed that you can have many bandpass filters for the whole frequency band of interest you would like to sample, and then take them and do the processing. So like that, several approaches, but right now, recently, like prime factor sampling, in the sense that you take the signal, and this is one of the recent work, not very recent, just some time back I have come across that, though I didn't pursue it very actively. So that is something like if you have a signal, you just sample, not like a conventional way of doing that. Say you sample at 0, 5, 10 like that, and you make your another sampling instant such a way that which is a co-prime number of the previous samples. So like this kind of co-prime sampling between two different streams of data, you can reconstruct a very accurate information than the same number of samples which you take in the normal uniform way of sampling. So this kind of how to align your samples with some co-prime sampling and like another way of arranging the sample in such a way that they reform into different spatial dimension, or they reform into different spatial dimension. So like that, there were several works based on that, but I have not very recent works and all. I have not come across anything since I didn't do that research part very intensively.
No issues, sir. Makes sense. Makes sense. Thank you so much.
Yeah.
Okay, now all participants are requested to turn on your camera for the group photograph. Kindly switch on your camera. फाइल वहां रख दो. 2 मिनट बाहर रुक जाओ, ठीक है.
Thank you, everyone.
Thank you, everyone. Thank you, sir.
Thank you. Thanks.
Thank you, sir.
Thank you, sir. Thank you, ma'am.
Yeah, thank you, Professor. Thanks.
Now there will be assessment test of day 2. The link